This is a lesson about hyperbolic functions. Hyperbolic functions are an extension of the trigonometric functions. So the first thing we should do is revise what we mean by the trigonometric functions. So if you have a look on here, I've got myself a unit circle. So this circle has a radius of 1. If you remember, what we found is that we can describe any point on the circle just in terms of its angle from the center. And we call that cosine theta, sine theta. So this point here is cosine theta, sine theta, or 0.92, 0.39. So as I change theta, the point moves around the circle. So we can describe the point anywhere on the circle with the by changing the value of theta. What we say is we have parameterized the circle. Parameterized means we've got a variable, a parameter, and that describes the circle. The circle has an equation, x squared plus y squared equals 1. Okay, so that's our quick review about the trigonometric functions. So what we're going to do now is we're going to extend those to the hyperbolic functions. Okay, so let me get rid of the circle. Here is a hyperbola. So a hyperbola, if you remember, has an equation, x squared minus y squared equals 1. Well, this is the standard one. Okay, so you might recall a couple of key facts about its asymptotes. The asymptotes will be located at plus or minus b over a. So in this case here, we've got a x squared minus y squared equals 1. And so the asymptotes are, we've got theta equals pi over 4. So this angle here is pi over 4 or minus pi over 4. Okay. So in exactly the same sort of spirit as before, what we're going to do is we're going to describe any point. We're going to describe any point on the hyperbola by using a parameter, in this case t. So as I'm going to move the value of t around, that's going to change where we are on the hyperbola. So we call the coordinates hyperbolic cosine t, cosh, hyperbolic sine t, sinh. Now there's a few different ways of saying that. I prefer to say hyperbolic cosine, hyperbolic sine. So as we kind of move the value of t, we're moving the value of where we are on the circle. So this is kind of a definition. So in the previous example, let's go back to the circle. What we said was, I can describe anywhere on the circle by the parameter theta, and those point is cosine theta, sine theta. It so happens that theta is the angle. Okay. Likewise, we're going to describe anywhere on the hyperbola, hyperbolic cosine t, hyperbolic sine t, cosh t, sinh t. Okay, so I can change the value of t, and it describes where on the hyperbola. Now you might be thinking, well, is t some sort of angle? Well, the answer to that is no. Okay, the t is not related to an angle this time. Now you might want to know why. Very quick, I don't want to get too bogged down by this, but you can see that actually, if we try to use an angle, you're going to end up stuck, because after pi over 4, there's a big gap before the next one. Okay, so actually t in this case is not an angle. Okay, but regardless, it still describes the circle. Okay, so the coordinate of a point on the unit hyperbola, x squared minus y squared equals 1, well, that's cosine, hyperbolic cosine t, hyperbolic sine t, cosh t, sinh t. Now you might be thinking, well, what about the other side? Well, I can simply get to the side by having minus cosh t sinh t. So as you can see, if I trace this around, I can get anywhere on the other side. So what we've done here is we've parameterized the hyperbola. Okay. So we've just parameterized the hyperbola, and we parameterized, so let me just make a statement this. A point on the unit hyperbola, so with equation x squared minus y squared equals 1, has coordinates cos t sinh t, hyperbolic sine, hyperbolic cosine. So the hyperbolic is referring to it's on a unit hyperbola. So just a quick sketch of that. So if I've got my axis down here, something along the lines of this. So really we're referring to this branch of on this side here. So this has coordinates cos t sinh t. Okay. Now if we want the other side, that's no problem. The other side, so I'll just put that here. The other side, or the other branch, is just going to be minus cos t comma sinh t. Now you might be thinking, well, surely all you've done here is given a name to something, and you might be right. That's all we have done at the moment. We've just said that the points here parameterized some value of t tells us where we are on a unit hyperbola. And again, I'm going to make the point that t in this case is not an angle. It does have actually a geometric interpretation, but I'm not going to go into it in this video. I have a more in-depth version of this video that I might pass to people if they want to. But it's not an angle. For this circle, the theta it was the angle between the x-axis and the point, but here it's not going to be. The t is not an angle. It's just a parameter. It's just a parameter. To help us describe where we are. I say it does have a geometric interpretation, but I'm going to leave that just for now. Okay, so the next question that you might be having to yourself is, so kind of what? So what really? We've kind of given a name to a point, cos t sine t, okay? We don't really know anything about hyperbolic cosine or hyperbolic sine, but perhaps we can put these functions in terms of functions that we already know. So in other words, let's ask a question. Do we know if we can write the hyperbolic functions in a better way? What? In terms of things we already know. So do we know, is there functions that are there functions that we already know that we can write these hyperbolic cosine, hyperbolic sines? And the answer to this question is definitely yes. Okay, now you might think that these are going to be quite crazily, well, like who would have ever thought of this? And that's a little bit because of the way I've skipped over the parameterization. I've got more in-depth videos that you can naturally arrive at these conclusions, but I'm just trying to go for really straightforward for this one, simpler. So cos t is equal to e to the power t plus e to the power minus t divided by 2. Okay, so we already know what e to the t is and e to the minus t. So we now know, in terms of things that we already know, we've got cosh t. Likewise, hyperbolic sine, sinh t, is going to be quite similar to this, e to the t minus e to the minus t, all divided by 2. Okay? So what I claim is, if we recall, the whole point of cosh t and sinh t, they solve x squared minus y squared equals 1. So I put that a different way. Cosh squared t minus sinh squared t is equal to 1. Okay, so what I'm going to show you now is that, in fact, yes, if you take these as our definitions of cosh and sinh, then they will fulfill this one here. So I'm going to take that a new page to do that. So we're going to show if we've got cosh t equals e to the t plus e to the minus t, all divided by 2, and we've got sinh t, which is going to be e to the t minus e to the minus t over 2, then we're going to have cosh squared t minus sinh squared t. Hang on, put that square in the wrong bit there, haven't I? Sinh squared t equals 1. In other words, x squared minus y squared equals 1, which was the hyperbola. Okay, so let me just show you how that's going to work out now. So we're going to basically plug these things in. So we'll have cosh squared, well, that would be e to the t plus e to the minus t, all divided by 2 squared, minus the sinh t, which would be e to the t minus e to the minus t, all divided by 2. Right, so, and squared that. So if I'm going to write this out longhand, I would have e to the t plus e to the minus t divided by 2 times by e to the t plus e to the minus t, all divided by 2. Okay, and then I'm going to subtract e to the t minus e to the minus t, all divided by 2, times by e to the t minus e to the minus t, all divided by 2. Okay, so this looks a bit daunting, but it's not going to be too bad. So let's do this one here, this side here first. So we're going to have e to the t times e to the t. Well, we can bring up the quarter. The quarter is not really going to do anything, isn't it? So let's just do half times a half is a quarter. So we'll bring that out. Okay. We're going to have e to the t times e to the t, which is e to the t squared, or e to the 2t. So maybe I'll put e to the t squared is going to be e to the 2t, isn't it? Okay. Right, now we're going to have an e to the t times e to the minus t. Well, e to the t times an e to the minus t would be e to the 0, which is 1. So this is going to be plus a 1. E to the minus t times an e to the t, well, that's plus another 1. And e to the minus t times e to the minus t is e to the minus 2t. Subtract. The quarter is going to come out again from this side. So e to the t times e to the t is e to the 2t. E to the t times minus e to the minus t, well, that's going to be minus 1. Plus positive here, so maybe I should put a bracket there just to be clear what we're doing. So e to the t, e to the minus t minus e to the minus t times e to the t is going to be minus another 1. And this is going to be a plus e to the minus 2t. So I've got a closed bracket there and a closed bracket here. Okay, so let's just have a think. I don't want to write all this out, and you can check if you really want to afterwards yourself, but let's just kind of go for it. We've got a quarter is just going to be a factor of everything, so we can pull that to the front. We're going to have e to the 2t minus e to the 2t, so they're going to cancel out. Okay, so the e to the 2t's are definitely cancelling out. That's going to cancel with that one. We're going to have an e to the minus 2t subtract an e to the minus 2t, so that's cancelling out as well. We're going to have a 1 plus 1 is 2 here, and I'm going to have a minus 2 here, but I'm subtracting a minus 2, so it's going to be plus 2 here. So 2 plus 2 is 4, and a quarter of 4 is 1. So what we've just shown then is indeed, definitely, we've just shown that if we take cosh t to be e to the t plus e to the minus t over 2, and if we take sine t, sinh t, sorry, as that definition, e to the t minus e to the minus t, then we're going to get 1, which is what we wanted for our parameterization of a hyperbola. So that's what we wanted. So if you wanted to, you could just think to yourself, well, this was a really good guess, okay? Or just from sort of playing around with exponentials, you would eventually stumble across this. There is a more direct way, as I said before, but it's a lot more complicated, and I don't want to do it now. Okay, so just to kind of recap where we're going again. So we've got cosh t, sinh t, oops, make that a bit better, sinh t. Those are the coordinates on the x squared minus y squared equals 1. So as we kind of have a little sketch again, just to keep going through the same things, reminding you that if this is the circle, or this is the hyperbola, sorry, coming down like this, then we're talking about here. Okay, so this is your cosh t, your sinh t. Okay, so, well, that's kind of like, we've got sine, cos, and tan, and now we've got cosh and sinh. Is there the next question should be on your brains is there a hyperbolic tan? Well, the answer to that is yes. So what's the sensible definition? You could probably guess. Okay, well, if you recall that sine theta over cos theta is tan theta, that should give you some inspiration. Okay, so we're going to have define. So we're just going to say, we're going to state this. This is what we're going to state. We're going to say hyperbolic sine t over hyperbolic cos t is going to be the hyperbolic tan of t. Okay, so that's just by definition. So can we write this in terms of exponentials as we did before? Well, yeah, we're just going to plug the things in, haven't we? Okay, so let's plug in hyperbolic sine would be e to the t minus e to the minus t, all divided by 2, divided by e to the t plus e to the minus t, all divided by 2. Well, okay, the 2's they're going to cancel out. We're just going to end up with e to the t minus e to the minus t over e to the t plus e to the minus t. And that can be our version of hyperbolic tan. So that's going to be tan hyperbolic. Okay, you might be thinking, can you tidy it up somewhat more? Well, probably, but I'm not going to now. You could, for example, times this is a 1 over e to the t, isn't it? So I could times everything by e to the t and sort that out. But again, that's just, you could spend all day changing this into different forms. Here's just a basic one. So I'm going to add that to our list of things. So summary. So far, cosh t is e to the t plus e to the minus t over 2. I like to think of this as the average. If you remember the average, then it's kind of obvious then, because it's the average of these two. The sine hyperbolic is going to be the same thing, but subtractions, minus e to the minus t over 2. The tan hyperbolic is going to be the sine hyperbolic divided the cosine hyperbolic, so that would be e to the t minus e to the minus t divided by e to the t plus e to the minus t. Okay. Do these all have inverses? Yes, but I'm not going to do them now. Okay, so there's lots of things that we can do with these. Taylor series, Maclaurin series, all the sorts of things that you've done in the past, graphs, the whole lot, they equations, all of these, you know, anything that you've done, pretty much anything that you've done with trig functions, you're now going to do with these. So anything you've done with trig functions, then you're going to do with hyperbolic ones. So I would really encourage you to remember as much as you can in terms of identities for this trig ones, because many of them are very similar to the hyperbolic ones. So it's almost like a 2-for-1. Not quite, they're not quite the same, but there's a lot of them that are very similar. So for example, x squared, sine squared plus cos squared equals 1 is very similar to cos squared minus sinh squared equals 1. Not exactly the same, but they're very similar. Okay, so I'd encourage you to review them. Okay, so what's next? So we've got our basic definitions. Let's do some basic calculations. Okay, so we've got some basic calculations. Right, suppose I wanted to work out, let's do hyperbolic tangent of 0. Well, if I wanted to work out what this is, then what I'm going to do is I'm going to plug into our definition. So that would be, if I recall, the hyperbolic tangent is equal to e to the t minus e to the minus t over e to the t plus e to the minus t. So here our t is going to be 0. So that's going to be e to the 0 minus e to the 0 divided by e to the 0 plus e to the 0. Well, that's going to be e to the 0 is 1, so 1 minus 1 over 1 plus 1. 1 minus 1 is 0, divided by 2 is still 0. So the hyperbolic tangent of 0 is 0. And I could let you to do this with a number of different examples. I'll maybe do one more example. How about do a little bit more of an advanced one? The hyperbolic sine of the natural log of 3. Okay. Now you might be thinking, well, the natural log of 3 is going to be awkward, but actually it really helps us. So recall that the hyperbolic sine of t is equal to e to the t minus e to the minus t all divided by 2. I would really strongly suggest that you try and commit these to memory. I know that you might be thinking it's a lot of memory power, but it's a bit like learning your times tables. Yes, you can look them up in a times table, but that doesn't really help you solve problems with factors, does it? You know, when you're trying to factorize something, you know all the times tables in your head, and so you can factorize with ease. If you had to look up every time what goes into 48 and from a times table, then that would severely, limit your ability to do factorization. And in much the same way, the more that you can commit these into brain so that they're just there, the more time you can spend on actually solving the problems, which is really kind of where all the marks are. So let's plug these straight into our definition. So we've got the hyperbolic sine of the natural log of 3 would be e to the natural log 3 minus e to the minus natural log 3, which is all over 2. Well, the e to the natural log 3 is just going to be 3. Now then, recall that when we've got use the power law for natural logs, so this is really minus 1 lot of natural log of 3. So I could write this as subtract e to the natural log of 3 to the power minus 1. So this is the power law. So remember the power law for logs. Logarithms. So that's what I've done there. Okay, so I've brought this power -1 up top there, divided by 2. And the reason for doing that is now I can use the e's and the natural logs cancelling. So this becomes 3 subtract 3 to the minus 1 over 2, which is really just simple now. 3 to the minus 1 is a third, so 3 subtract 1/3, all divided by 2. And if you want to work it out, I believe the answer is 4/3. Okay. So the natural log, the hyperbolic sine of the natural log of 3 is 4/3. Okay. Well, you might be thinking, does my calculator help? Can my calculator help? Well, yes, there is some buttons on your calculator that does this for you. Okay, here I've got a picture or an emulator of your class quiz. If you click on options, then number 1 is hyperbolic functions. So if I click on 1, then I've got the options for hyperbolic sine, hyperbolic cosine, hyperbolic tan. These are the inverses, as you might expect, but we're not going to look at those today. Okay, so the hyperbolic sine, if I click on that, number 1, press 1. So if I type out the hyperbolic sine of the natural log of 3, and put my brackets on, hopefully we said it was 4/3. There we go, 4/3. So, and the tan of 0 is, let's try that one, so I'll clear. So options, number 1 for hyperbolic functions, number 3 for tan, 0, and I close my brackets. There we go. So you can use your class whiz to work out the hyperbolic tangents. So I'm going to make a little note of that. Use your class whiz where possible. And I'm going to put this in red. But you are smarter than the calculator. And for heaven's sake, don't just think, oh, well, this is just one of those calculators. So, switch my brains off, just use a calculator all the time. If you do that, then you're going to end up in problems later on. Suppose that the examiner gave something where you couldn't put it into a calculator. So maybe it says, work out the sine of the hyperbolic. Let me give you an example. Suppose they said, show that the hyperbolic sine of 2b is equal to something or other. Well, you can't just whack that in a calculator now. So don't just think, use your calculator. Yes, definitely use your calculator, but don't think your calculator is going to do the work for you, because it's not going to. I might do a video at some stage in more depth of how to derive these things, but it requires a lot of integration and areas. it will turn out that the parameter t is something to do with area, not angle. Okay, well, I'm going to stop the video here and I'll set some work for people.